My name is Louk Rademaker. I'm 36 years old. I'm originally from the Netherlands, and I did also my PhD there. After that, I did postdoctoral research in Santa Barbara in the United States and in Canada. And recently, I started as assistant professor at the Department of Quantum Matter Physics in Geneva. So my drive is to really understand fundamental properties of nature. But the most common approach to do that is to look at tinier and tinier parts of the nature to understand what the stuff around us is made of. But for me, that's very unsatisfying. For yes, you can understand that the world is made out of quarks, for example, but that knowledge doesn't tell you anything why the grass is green and the sky is blue. It also doesn't tell you why you can safely stick a pencil in an electrical socket but not a fork. So what really quantum matter physics is about is the idea that not the parts themselves, but how they all work together plays a role in defining that material. In particular, most of the technology that we have around us consists of, for example, semiconductors, and we understand those materials extremely well at the moment, because there the electrons are barely talking to each other. Instead, what fascinates me is a growing class of materials where we do not understand what drives them and what causes the phenomena there. And that is because there the electrons are very strongly interacting. The most famous example of that is the cuprates. Those are the best known superconductors that we know, but we still don't know why they even superconduct. There's also other exotic phases where, for example, electrons break into tiny parts, and that kind of things really define what it means to be a material, and that is what fascinates me. So about 5 years ago, a new revolution happened in the field of quantum matter physics. Because before, you just needed to find a material and hope that it had some interesting properties. But with the advent of twisted materials, we can really change and design materials that have the desired properties that we want. The most famous of them is twisted bilayer graphene. Graphene is a single atomic layer of carbon atoms, and if you put two of those layers on top of each other and deliberately misalign them, you get this beautiful geometric pattern called a Moiré pattern. But what's more important is that whenever such a Moiré pattern arises, you can have any type of interesting electronic phases. For example, superconductivity. There's also been the so-called quantum anomalous Hall effect observed, and many more. Now, I'm a theorist. There has been a lot of experimental progress in these materials, but for many of the observed phases, we do not understand why they arise. For example, we still do not know what causes the superconductivity in twisted bilayer graphene. That is among the questions that I want to understand. So I'm going to hire, thanks to the starting grant that I got, 2 students and a postdoc, and together we're going to do theoretical research trying to understand these new phases in all these twisted materials. Now, as a theorist, what that means is we sit down, we come up with an idea, and then we calculate what the observable consequences of that idea are. And then we talk to our experimental friends, and if we're lucky, they find something consistent with our predictions, and otherwise, well, we have to come up with a new idea. My research project will have 2 fundamental pillars. One is we really want to understand better the so-called MOT metal insulator transition. This is a transition where a material goes from conducting electricity to being insulating as a consequence of an increased interactions between the electrons. And that's a transition that's still not really understood. The other pillar will be the search for exotic phases in these twisted materials, such as possible spin liquids or topological superconductivity. Those are just tip of the iceberg of exciting new phases that you can realize in these materials. And who knows, maybe we can, at some years in the future, have twisted materials in your new technological applications. I want to thank my host institution, the Department of Quantum Matter Physics at the University of Geneva, and of course the SNSF Starting Grant, which I got, which is a transitional measure to replace the ERC grants.